Hello, everyone. My name is Chase Coley,
My name is Khalil Adams.
and we will be presenting our research for the Renamilla Case Symposium.
Research context. So basically what we're working with is data from optical parallel plate avalanche counter. Um, how this works is basically the Facility of Rare Isotope Beams uses this to investigate and basically get conclusions about the nucleus using the data collected. The facility will shoot a beam at the OP pack, which basically there's a little space in between. There's a little middle space in the OP pack called that has scintillator material that the beam is shot at, and the diodes basically pick up data on the particles that hit them and give us numerous insights that allow us to derive conclusions and ultimately let us localize the beam and essentially give it coordinates. And the problem we're facing is that we want to make those coordinates as accurate as possible.
So what you see here are graphs that are made from the data that we get from the OP pack. So each graph corresponds to a side of diodes. So there are four sides, four graphs. As you can see, in the middle, there's another graph, and that is basically telling you the distance between the particle and each side. So on the left side, we see that our particle is 12 millimeters away from our left side. So our graph is very skinny, and the number of photons detected is very high. The reason for this being is the beam that comes off has to travel through, it's kind of like you saw in the last picture, it's like a gateway, has to travel through the gateway to hit the diode. And when it's closer, it's gonna hit those middle diodes, but it's not gonna hit the outside ones because of the angle. So the beam is not traveling all the way through the gateway and it's not hitting the diode. But on the other side, as you can see, when when the right side is 82 millimeters away, our data is much more spread out. It's hitting more of our diodes and there is a less number of photons detected because the beam isn't as strong once it hits those once it hits those diodes. And then when our top and bottom sides are equal distance away from the particle, you see that our graphs are pretty similar. They are both hitting those first 5 to 10 diodes, and the number of photons detected is around the same, and that's because they are equal distance from the particle.
How we want to improve on this is machine learning. What is machine learning? Machine learning is basically how the machine learns and basically gets better with interpreting data. How we went about this, the first step was to understand that this is a supervised learning problem. What does that mean? Supervised learning essentially means, in the context of this problem, when we feed the machine data, we're not just feeding it data without the answers. We feed it data, it makes guesses, and then it looks at the answers that we gave it, which are correct, and basically fine tunes itself to get closer and closer to matching those answers. And this specific OP pack problem is a regression problem, meaning that essentially when we give it data, it's continuously outputting Y values. It's not a classification problem, which basically you give it the data and it's either 0 or 1. The regression problem, you give it data and it puts that data in an equation and you're continuously outputting Y values. There are multiple Y values. And you can see that there's a little trend line up here that basically is trying to match the trend as much as possible of these different Y predictions.
So FCNN stands for fully connected neural network. And that's what you see on the right in that little diagram there. And essentially what a neural network is there are algorithms that are used to try and minimize the brain, which is what the neural network is. It's like the brain of the AI. And what we're trying to do is move from the left, which is our input layer. We move from our input layer to our output layer, which is on the right. And what that is called is forward propagation. And essentially we're using forward propagation to move through and minimize the brain. And fully connected neural networks are structurally agnostic, meaning that there are no special assumptions about our input values.
How we continue to minimize is gradient descent. So what you see here is a landscape, a graphed landscape, so to speak. And what this is supposed to mimic is the error that we produce using the machine. And what we want to do is move from those higher parts of the landscape to the lowest possible point of the landscape, the lowest optima, right? And so what we do is we run through, we notice how high the error is, and we keep fine tuning ourselves until we get lower, 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 lower to the absolute lowest we can go. And when we're at the lowest point, that means our margin of error is the lowest, and thus also means we are getting the most accurate results possible with our fully connected neural network.
So, as Khalil said, basically what we're doing with gradient descent is we're trying to get lower and lower and find that minimum. So, in the loss curve graph, what we're looking for is for our graph to continuously go down, get lower and lower. If it starts to go up, that means that we have overstepped and we start to go up um, with our gradient descent, which is not what we want to do. We want to find the minimum. So, essentially, the loss curve is the margin of error from our predicted values and the true values that we got from our training. And the validation curve is from the validation loss, my apologies, is from the data that we set aside that we did not train on. And that's again the margin of error. And what you want to see is you want to see them stay close together. You don't want to see them get too far apart. And if they ever plateau, that means you're done training, you found your minimum, and that's where you want to stop. So we trained for 150 epochs, which 50 epochs longer, of course, and it plateaued, which means it plateaued right after 100. So we decided 100 epochs was as long as we needed to train it, and this is basically a very good graph and what you want to look for in graphs.
These are our residual graphs, and for the sake of not overcomplicating things, I'm just going to explain what these essentially are doing. The y-axis is the number of predictions for each margin of error. So you see that these graphs are centered around 0 for the most part, which means that for most of our predictions, we have a very, very small margin of error. The X predictions never really reach negative 0.1 or 0.1. So the margin of error is sort of at a 0.00 stage. Like most of the X errors are going to be that type of margin of error, which is really, really good. It's a good degree lower than what we were seeing previously. For the Y residual, it's a little bit thicker at the base, but it's still pretty squinty. It's still pretty skinny. We see a lot of negative 0.1, a little bit over that. That's the highest margin of error. But from what we're seeing, it's still centered around 0 for the most part, and a lot of predictions being made with minimal margin of error, which is really good for us. Ignore the Gaussian fit line. We just couldn't reproduce these graphs because a lot of AI iterations and doing this, it's a little bit random. So we didn't know if we could reproduce these results. And so the Gaussian fit is just something we couldn't take off of these tables. So completely ignore that.
So what you're seeing here, so the top two graphs are our predictions for X versus our true values for X and Y, and our prediction for X and Y based off of the AI training, and the bottom two are off the Gaussian fit formula. It's the X and Y prediction and true values as well. So for the top two graphs, these are some very good graphs. These are kind of what you want to see. The line you're seeing in the graph is kind of X equals Y, so it's just following right up. The slope is continuous throughout and it's equal. So at negative 40, you see that's our x-axis, our true values. So we want our prediction to be negative 40 as well, which will end up right on that line. So basically, if a dot ends up on that line, then our predictions equal our true values, which is what we want. And so for the top two graphs, that's what we see. For the bottom two graphs, we see the same thing except for these little groupings of dots that you see above the line on the bottom left and then above and below the line on the bottom right. These are errors. We have not figured out why we've gotten these errors yet. Otherwise, we would have used some better graphs for this presentation. But yeah, these are errors that we don't want, and we need to go back through our notebooks and kind of debug and figure out why we are getting these groupings of dots because They shouldn't be there. All the other predictions versus values are accurate, but those are just kind of thrown in there, and we need to figure out why.
Future work, what's next? We've had a lot of fun training this machine over the data that we've had, and getting it to basically find lower and lower optima and keep getting closer to being more and more accurate. That's been very, very exciting for us. And the next step for us is we really want to work on more complicated data that resembles closer to real life, so that we can have some like real impact, and we can really help the facility of rare isotope beams by building on the research that was given to us. In terms of finding out what's up with the Gaussian fit, that's less involved with the artificial intelligence portion, but it does provide a clear comparison between the two methods, which is going to be beneficial when presenting the research at a larger scale. And that's all we have for what's next in terms of future work.
And so lastly, our acknowledgements. So we want to thank Alpha, our peers. They've helped us out a lot. We were new to the program this year, and there were a lot of people who returned, and they kind of just helped us with learning some of the basics. We want to thank Michelle and Ragu, who gave us the resources to learn everything we learned about our research project, and have also answered any questions or helped us find the answers to any questions we've had throughout the process. We also want to thank Yasid, who is actually the doctor at Michigan State University, who is at the facility for rare isotope beams, who is getting us the data. We want to thank him for all his expertise on the OP pack and everything he taught us. And then we also want to thank Kate Roberts for the great work she put in, because we were allowed to build off of that. So we want to thank her, and she left all really clear instructions of how everything works, and it was like pretty easy to go through and figure out how everything works. So we want to thank her for that.
And finally, we want to thank all of you for coming out and listening to our presentation about our research, and I hope you all have a great day.